So here we have one of those problems that relies on a geometric meaning for a partial derivative. And specifically, the interpretations of the derivatives the partial derivatives that we need for this problem are that, for example, partial f partial x is a rate of the increase in the height of f when x increases by a small amount, and partial f partial y is the rate of increase in the height of f when y increases. And believe it or not, we've been given enough information to determine whether both of these are either positive or negative at the given point P. Now, the first thing that we need to do is remind ourselves of the conventions that x, y, and z increase in the direction that the arrows on the axes point. So, in other words, they increase in the directions that I'm pointing here. So if we are at the point P, okay, and we increase x by a small amount, what we see is that the corresponding change in the value of the function is positive. It is a positive change in the height of the function, and what this tells us is that partial f partial x is in fact positive. Another way to think about this without drawing changes in x and changes in f is if we're at the point P, well, we're taking the partial derivative with respect to x, and we know that that means that we hold y constant. So if we hold y constant and increase x, is the function increasing or decreasing? Well, it's pretty clearly increasing, so that increases our confidence. Yes, that partial f partial x is positive. It's greater than 0. Now, the reason I wanted to move away from drawing changes in x and changes in f in the last case is that it's sort of difficult. That's the problem with graphing surfaces, is that oftentimes we're left to visualize them two-dimensionally, which has its fair set of challenges, and it's not always easy to see the things that we need to see in them. So anyways, let's just imagine that we're talking about partial f partial y, okay, the derivative of f with respect to y, which means that we are holding x constant. And if we hold x constant and increase y, what happens? And imagine that, say, we're walking on this actual surface according to these specifications. If we hold x constant and increase y, what is happening to the function's height? Well, it plummets. So, in other words, it decreases, and not just by a little bit. So here we can see that partial f partial y is less than 0. So I like this problem because partial f partial x is positive. So if you walk along the surface in the positive x direction, holding y constant, the function is increasing, okay? But if you hold x constant and walk along the function in the direction of positive y, increasing y, then the function value is negative. So we haven't been given enough information here to compute specifically what these derivatives are, how positive partial f partial x is. We can't really quantify that. And partial f partial y, well, we can tell that the height plummets, but we don't have any values with which to compute a specific value and pin a specific value on that rate of change. But we are given more than enough information to determine whether these rates of change are positive or negative. And I want to point out that, say, the difference quotients and all these rules that we have for computing derivatives symbolically are not helpful here, but a lot of the same principles are at play. Holding one variable constant and changing or increasing the other, we use that several times in this problem. So they are different sides of the same coin, but a lot of the same ideas go into derivatives, whether you're looking at them symbolically, computationally, right, or graphically and geometrically. Anyways, hope that made sense. See you in the next video.